In this video, we'll understand the importance, the geometrical meaning, and the real-world application of integration. Instead of starting with formulas, we'll explore integration through a story, a fascinating historical story inspired by Archimedes. Through this story, we'll see how complex shapes can be understood by adding many small parts together, and how this idea became the foundation of calculus. Hi, welcome to this video on Integration Simplified by Maths Simplified. So let's begin by understanding the concept of integration through a story.
Long ago, in ancient Greece, a powerful king possessed vast bars of gold. He wished to turn them into shining coins, but he faced a problem no one could solve. Gold could not be counted by weight alone. Coins had curves, they had shape, they had volume. The king summoned the greatest scholars of the land and declared,
"Find me a way to know how many coins I can mint from this gold. Fail, and you will be beheaded."
The scholars worked day and night. Scrolls were filled, shapes were drawn. But no one knew the area of a circle. No one knew the volume of a cylinder. Among them stood a quiet man. His name was Archimedes. He did not search for a formula. He broke the circle itself. He shaped clay into circles. He sliced them into countless thin pieces and rearranged them side by side. Before his eyes, the impossible happened. Now we shall briefly see the illustrative proof of this. The broken circle became a rectangle. Its length was half the circumference of the circle. Its height is the radius. Archimedes uncovered the secret of the circle by breaking it into countless pieces. But his work was not finished. Area was only the beginning. Gold did not lie flat. It rose. It filled space. So Archimedes turned from surfaces to depth, from area to volume. By extending area through height, he discovered volume. Area multiplied by height became space. With this insight, he measured the volume of a single coin. Then he calculated how many coins could be minted by dividing the total volume of the king's gold by the volume of one coin. The impossible was solved. The king rewarded Archimedes with honor and gold, but his true reward was an idea that would echo through mathematics for centuries.
Now we shall understand the definition and geometrical meaning of integration. Consider a function f of x drawn as a curve on the xy plane. The horizontal axis represents x, and the vertical axis represents the value of the function f of x. Now look at the integral. Integral from 1 to 3 of f of x dx. The limits, 1 and 3, restrict our attention to a specific region along the x-axis. Only the area under the curve between x equals 1 and x equals 3 is considered. This shaded region represents the area whose value we want to calculate. To calculate this area, we divide the region into many thin vertical strips. Each strip has a small width called delta x. Let us focus on one strip. The height of this strip is given by the function value f of x. Therefore, the area of one strip is f of x multiplied by delta x. Adding the areas of all such strips, we obtain a summation. This summation approximates the total area under the curve. Now, as we increase the number of strips, each strip becomes thinner. The rectangles fit the curve more accurately and the approximation improves. When delta x becomes extremely small, we write it as dx. In this limit, the summation becomes an integral. Thus, the integral of f of x from 1 to 3 represents the exact area under the curve between these limits. Integration is nothing but the limit of a summation of infinitely many infinitesimal strips. Integration has many important applications in engineering. Let us look at some key examples. First, work done by a variable force. In mechanical engineering, springs follow Hooke's law. The work done in stretching a spring is calculated using integration. Work equals the integral of force with respect to displacement. Second, fluid force on a dam. In civil engineering, water pressure increases with depth. The total force on a dam is found by integrating pressure over the height. Third, electric charge from current. In electrical engineering, current is the rate of flow of charge. The total charge is obtained by integrating current over time. Fourth, beam deflection. In structural engineering, bending of beams depends on bending moment. Beam deflection is obtained by integrating the bending equation twice. Fifth, flow rate in a pipe. In mechanical and chemical engineering, fluid velocity varies across the pipe. The total flow rate is calculated by integrating velocity over the cross-section. Finally, energy of a signal. In electronics and communication engineering, signal energy is found using integration. It is equal to the integral of the square of the signal over time. I hope you enjoyed this video. If this story helped you understand the concept of integration, don't forget to like, share, and subscribe to Maths Simplified. Thank you for watching.